and m is the distance between beginning of the frames. So I take m is equal to n by 3 for reference purposes, and frames are calculated by MATLAB.avi functions, normal functions. So what I see is when the n is very low, then its time domain is defined very good. You can see that its time domain resolution is very high. And when I take n is equal to 512, its frequency domain resolution is very high. So we need to take such a value that both the resolutions are equally given the weightage. So we take n is equal to 256, then we can check it from this figure that the time domain as well as frequency domain are in high resolution. So it completes our demand. So we take the number of the sampling frequency rate to be 256. This was just to show that why we have chosen those values. Now next is the MEL space filter bank. Now this filter bank depends on the sampling rate basically. Now what happens is that when we multiply the signals, that is the signal that we obtained in linear plot and logarithmic plot, those are calculated by windowing and then FFT on them, means dividing them into frames, because all the information we just extract some part of it with the help of windowing and FFT, and then when we multiply it with MEL spaced filter bank, this gives us what we say is MEL space wrapping, MEL frequency wrapping. So we can see from the description that before the signal was MEL wrapped, it was shown like this, and when it was wrapped, while wrapping, what I mean to say is when it has been divided into the frames, then it is multiplied by the MEL spaced filter bank. Then you can see that here the values which we are seeing are of very low resolution, and as soon as we apply the MEL substrum filter or multiply it by MEL space filter bank, then its intensity increases. So we can see that yellow and red part are visible more. So if we take logarithmic now in it, then we can see that after taking logarithmic, its resolution with that we get are more intensified. So we are using MEL spaced filter, and this process is MEL frequency Cepstral coefficient, which we are calculating, MFCC. Now after this MFCC process, there is a process for what we are using for matching, means this was for feature extraction purpose, means till MEL frequency Cepstral coefficient are calculated, our features are extracted in MFCC form. Now in order to compare two voices, we are using here vector quantization concept. Likewise, we can see 2D plot of acoustic vector of any signal. One signal means there are option of showing in one signal, two signal. Let us see one signal, let us say for signal 4. Now these are just the vector points, data points. These data points are of 5th dimension and 6th dimension, just for the sake of plotting and showing you the data points. Likewise, you can see these are the data points of the signal 4, that is the user number 4 in the test folder. Now if I look at the signal number 5, these varies from signal to signal, or how the way the person speaks, means we are now showing you the data points, but collectively organizing all the data points and using them for comparison purpose is quite hectic. So what we do is we apply vector quantization. Likewise, you can see here the signal 4 data points are denoted by red circles and signal 5 data points are by the crosses. So you can see that these two speakers are different as their data points do not coincide. What we are using here for the matching is vector quantization. Likewise, let me show you vector quantization code word. In train folder, I am showing you one signal, or let me show you the user database, the one storing Anupam's voice, which I have already shown you. Yeah, it took some time. This is Atom processor. Now you can see this speaker 5 points, data points are shown by the crosses, and delta here shows the centroid values.